Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my T.Y.B.Sc Analytical Chemistry class. Student, in previous lecture we discussed the instrumentation of flame atomic absorption spectrophotometry as well as we discussed the working of flame atomic absorption spectrophotometry. Under this study, we discussed the use of chopper in the measurement of the absorbance of the gaseous state atoms present in the flame. Student, in today's lecture, we discuss the different types of interference that occurs in atomic absorption spectrophotometry. Similar to flame emission spectroscopy, there are 5 to 6 types of interference that likely to be occurs in atomic absorption spectrophotometry. First of all, we discuss what is interference. Interference in flame atomic absorption spectroscopy. Interference in flame atomic absorption spectroscopy is intended to all possible difficulties that affect the absorbance signal of the analyte element. Therefore, similar to flame emission spectroscopy, interference in flame atomic absorption spectrophotometry is intended to all possible difficulties that affect the absorbance signal of the analyte. The first type of interference in flame atomic absorption spectrophotometry is a spectral interference. Spectral interference is again related with the overlapping of the absorption line of the analyte element and absorption line of the impurity element, due to which the absorbance of analyte element found to be more and concentration of the analyte is found to be more, and that gives the positive deviation in measurement. Therefore, spectral interference in flame atomic absorption spectroscopy is defined as the overlapping of absorbance line of the impurity element over the absorption line of the analyte element, due to which the concentration of analyte is found to be more than actual it is present in the sample. Actually, similar to atomic emission line, no two atomic absorption line have identical wavelength, but interferences occur due to the closeness of this wavelength. Therefore, when emission line of analyte element and emission line of impurity element are nearer to each other, then it affects the emission reading as well as absorption reading of the analyte. Therefore, particularly in flame emission spectroscopy, Aluminium have an emission line 308.261 nanometer, and similarly the vanadium have an emission line 308.221 nanometer. Therefore, here aluminium cannot be determined in presence of vanadium, because here the wavelength difference is 0.005 nanometer, and therefore here this wavelength difference, lambda difference, in order to distinguish the resonance line of the aluminium and resonance line of this vanadium, we have to use the monochromatic system whose resolution is 0.005 nanometer, and therefore here a highly sophisticated monochromatic system, that is refracting grating, is required for elimination of this spectral interference. Similarly here, copper having emission line 324.754, and here europium having absorption line 34.755 nanometer. Those are very close to each other. Similarly here, a iron 271.903 and overlapping with platinum 271.908 nanometer. Similarly, mercury having emission line 253.652 nanometer, and here a cobalt 253.649 nanometer. Therefore, here the overlapping of this absorption line with this absorption line is easily takes place. Therefore, we cannot determine aluminium in presence of vanadium, copper in presence of europium, iron in presence of platinum, and mercury in presence of cobalt, or vice versa, cobalt in presence of mercury. Therefore, here this spectral interference we can remove by using a highly sophisticated monochromatic system which have a resolution up to 0.001 nanometer. Therefore, spectral interference in flame atomic absorption spectroscopy can be eliminated by using a monochromatic system having a resolution of wavelength. That means it has a capacity to separate a resonance line of this from this resolution of wavelength up to 0.001 nanometer bandwidth. And when such a monochromatic system is available, then we can determine aluminium in presence of vanadium. But here we have to require a diffractive grating which can isolate a narrow band pass of a wavelength which differs by a factor 0.001 nanometer. Now, second type of interference in flame atomic absorption spectrophotometry is a chemical interference. Chemical interference mainly occurs in flame atomic absorption spectroscopy due to formation of refractory materials or oxides. The chemical interference in flame atomic absorption spectroscopy mainly occurs due to formation of thermally stable compounds, those are called as refractory material, which does not atomize ideal temperature, and hence atomization process does not produce the sufficient number of atoms, gaseous atoms in flame. So the absorbance reading is 8 degrees. Absorbance reading or signal is 8 degrees. Therefore, chemical interference in flame atomic absorption spectroscopy is related with formation of thermally stable compound which cannot decompose to the corresponding atoms. Atomization process becomes incomplete. Number of atoms in the flame found to be less, and then the concentration of the analyte in the flame found to be less. Here, specifically the complexing ions such as oxalate, borate, and phosphate form such a type of compounds. Forms such a compound with analyte. Sometime in flame atomic absorption spectrophotometry, when iron is get converted into their oxides, then that also does not decompose. In determination of iron can be get converted into iron oxide, or determination of aluminum can be converted to Al2O3 aluminum oxide if we are using air acetylene flame for the atomization. Therefore, here ions are get converted into their oxides, and these oxides are thermally stable. Therefore, those cannot be atomized at that flame temperature, and therefore number of atoms in the flame that get decreased, that affect the absorption signal of the analyte. Here in flame atomic absorption spectroscopy, the chemical interference can be overcome by using a chemical interference in flame atomic absorption spectroscopy can be overcome by using a high temperature flame, so that the oxide can be get decomposed to that flame temperature. Otherwise the releasing agents such as EDTA or a spectroscopic buffer can be used for elimination of this chemical interference. Releasing reagents that reacts with the analyte element and that forms a compound which can be easily decomposed at a flame temperature. Sometimes a buffer solution also used for this purpose. In presence of that buffer, analytes get complex, but that get converted into corresponding atoms when it reaches to the flame. Therefore, chemical interference can be overcome by using either a releasing reagent or complexing reagent and spectroscopic buffer. Third type of interference is called as ionization interference. Ionization Flame atomic absorption spectroscopy occurs when ions are formed in atomization process. Atomization process should form atoms, but if atoms are get converted into ion does not undergo absorption in flame by irradiation provided by halo cathode lamp, and therefore here the concentration of analyte found to be less than actually it is present in the sample solution. Suppose for example we have to determine magnesium. For determination of magnesium should be converted into magnesium gas, and this magnesium gas when irradiated with a resonance line produced by magnesium halo cathode lamp, then it is given to the excited state. Then we measure the P and then P0, then T is measured, that is ratio of P upon P0. But when this magnesium from the solution is get converted to magnesium 2 plus ion, but here that does not absorb the radiation, that does not undergo the electronic transition. Therefore here we have to maintain this ion in an atomic form, or we have to convert this ion into the atom, a gaseous atom, and it can be done by adding a ionic suppressor in the analyte solution. The ionization interference in in flame atomic absorption spectroscopy can be overcome by adding a ionic suppressor which produces excess of electrons in the flame by its ionization, and hence the produced electron can easily reduce the produced electron easily reduce the analyte ion to atom. In this case, when we add excess of either lithium or sodium ion, then here sodium ions are formed and electrons are generated. These electron reacts with this magnesium 2 plus ion, and again here magnesium can be converted into magnesium 0, means neutral atom, by taking the electron. That is here in this case sodium acts as a ionic suppressor because its ionization potential is less than the ionization potential of magnesium. More number of electrons are present in the flame, then flame have a reducing nature. Therefore, ion cannot be get oxidized, it get rather reduced, and therefore ionization interference can be eliminated by adding a ionic suppressor in the analyte solution. This ionic suppressor have a low ionization potential. Next interference in flame emission spectroscopy is a background interference. Background interference in flame emission spectroscopy is related with unwanted radiation generated by the flame. The background interference in flame atomic absorption spectroscopy is related with the unwanted radiations from the flame. Actually, the radiations which are emitted by the flame are not exactly the same radiation emitted by the analyte. But here a radiation from the flame that enhance the sensitivity of the absorption line. And therefore here this will be the continuous potential error occurs in absorption measurement. Therefore this can be eliminated. The radiation interference or this background interference can be eliminated by aspirating a blank solution and its absorbance reading can be subtracted from the sample absorbance reading. And hence the unwanted radiation from the flame that can be eliminated. Fifth type of interference, that is called as analyte interference, and which is also known as the self-absorption. Analyte interference or a self-absorption. This interference occurs when concentration of analyte in the solution is more. The analyte interference occurs when concentration of analyte in the solution is more. Here, when analyte concentration is more, then the plot of absorbance as a function of concentration, we does not have a straight line, but that get bent at higher concentration. Therefore, such a type of deviation is occur when concentration of analyte in the flame is more. In flame atomic absorption spectroscopy, the radiant power which is generated by halocathode lamp is given onto the flame, where flame containing analyte atom that undergo a excitation, and when these analyte atom come back to their ground state, that emits a radiation. These radiations, when emitted by the analyte element in the flame, that absorbs the gaseous state atoms present in the flame of their own type and that undergo the electronic transition. Therefore, here, rather absorbing the radiation from halocathode lamp, these gaseous state atoms which are present in ground state level, that absorb their own resonance line, which is given by the analyte element present in the flame, and therefore here the emission intensity of this resonance line which is given from halocathode lamp, that does not affected in much more factor. This will be occur generally at higher concentration. But actually in case of flame atomic absorption spectroscopy, the concentration level is in ppb to ppm level. That means very trace concentration of analyte can be measured by using a halocathode lamp. But here, when analyte itself absorbs its own emission line, then emission line of this halocathode lamp is not absorbed by the analyte, then concentration of the analyte found to be less. This type of interference is called as a analyte interference. it can be reduced by measuring the analyte having very low concentration. Analyte solutions having low concentration. That means when concentration is low, we does not have here a deviation from the linearity, and therefore we can easily reduce the analyte interference or self-absorption interference simply by using a dilute solution where we obtain the linearity in absorbance and the concentration. Student, this is all about the different types of interference in flame atomic absorption spectrophotometry as well as remedies on that interference. After the study of different types of interference that likely to be occur in flame atomic absorption spectrophotometry, now we discuss the advantages and disadvantages of flame atomic absorption spectrophotometry or spectroscopy. Now, first important advantage, suitable method for qualitative analysis. Suitable method for qualitative analysis. In flame atomic absorption spectrophotometry, identification of analyte element is carried out by using a radiation source which gives the continuum radiation. Therefore, here continuum radiations are given on the flame containing sample atoms, and then a wavelength at which that atomic species absorbs, that resonance line is identified by the monochromatic system for identification of the particular analyte species present in the sample. But it is possible by using highly advanced monochromatic system whose resolution is 0.001 nanometer to 0.005 nanometer. Therefore, here a qualitative analysis can be done by means of a radiation source which gives the continuum radiation. Second advantage is that best method that is a highly selective method for quantitation of the analyte. Quantitation of analyte. That means we can measure a particular analyte in place of other, and that is called as selective method of determination of analyte. If we have to determine copper in place of nickel, then aluminium, and if we use a copper halo cathode lamp, then we does not have interference of nickel and the aluminium in copper measurement, because whatever the resonance line emitted by copper halo cathode lamp, those does not absorb by the impurities present along with the copper, and therefore the method of analysis is highly selective. Therefore, we can measure the concentration up to very trace level, that is up to ppb level, and therefore here we can say that the technique is highly sensitive. Sensitivity is related with the measurement of lowest concentration of analyte. If any method or any technique measures very low concentration of analyte, then it is said to be very sensitive technique. Therefore, AES measures a concentration up to ppb level, and therefore here it is a highly sensitive technique. So it is a highly sensitive technique for determination of analyte. Number 4, sometimes some element does not absorb the radiation power from the halo cathode lamp, then their indirect determination can be carried out. Therefore, indirect determination is carried out for analyte those does not absorb the resonance line. For example, suppose we have to determine chloride. Initially, chloride is reacted with silver ion and silver chloride precipitate is obtained. This silver chloride precipitate is converted into solution, and after that concentration of silver is determined for measurement of the concentration of chloride ion. Therefore, here indirectly we can determine the concentration of this non-absorbing species by using a absorbing species. In this case, chloride is reacted with silver ion. Silver chloride precipitate is isolated, which is then dissolved into suitable solvent. And by using a silver halo cathode lamp, we can measure the concentration of silver for determination of concentration of a chloride ion. Next advantage is that whether analyte have a different oxidation state, where it is Fe2 plus or Fe3 plus, but it measures the total concentration of analyte. Therefore, here analyte determination is independent on the oxidation state of the analyte. Therefore, it measures total concentration of analyte. But here finally, if it is Fe2 plus or Fe3 plus, it is converted to iron atom, or finally Fe2 or Fe3 plus is converted to gaseous state iron atom, and therefore which can be easily determined by this flame atomic absorption spectroscopy. Therefore, here the advantages of flame atomic absorption spectroscopy: qualitative analysis can be easily possible by using continuum source and using an advanced monochromatic system. System technique or method is highly selective because it can measure the concentration of particular analyte in place of other. Technique is highly sensitive, having a lowest detection limit. Very low or trace concentration of analyte is determined. Indirect determination of the analyte is also possible by using its reaction with the another element which absorbs electromagnetic radiation, and determination of analyte in flame atomic absorption spectroscopy is independent on the oxidation state of the analyte or material. These are the most important advantages of the flame atomic absorption spectrophotometry. There are some disadvantages. Number one, this qualitative analysis is possible with a highly sophisticated monochromatic system, which have a chromatic system, which have a resolution power up to 0.001 to 0.005 nanometer. Such a narrow line, for isolation or identification of such a narrow line, a highly sophisticated diffracting grating is required. That means that diffracting grating should have a more number of grooves for more dispersion of the electromagnetic radiation, so that it can be identified the specific line which is absorbed by that particular analyte element, and it is possible with a diffracting grating having very large number of grooves and more dispersion power. Second thing is that here it does not useful for quantitation of or quantitative analysis of many metals, non-metals and metalloids whose absorption line is below 150 nanometer. That means here we does not have a monochromatic system that can easily isolate a resonance line below 150 nanometer. Most of the non-metals, even most of the metals and metalloids have their absorption line below 150 nanometer. Therefore, their determination is not possible by atomic absorption spectrophotometry. If we have a monochromatic system which isolates such a type of radiation below 150 nanometer, then we can measure the concentration of that particular element using flame atomic absorption spectroscopy. Number 3, it does not provide a molecular information, chemical bonding. That information does not provided by the atomic absorption spectroscopy, because finally atom Finally, sample solution is converted into atom and atomic concentration is measured. Therefore, it is not related with the molecular structure of the particular substance and it does not have a molecular structure. Number 4, it is a destructive technique. Destructive in the sense sample recovery is not possible. No sample recovery and therefore it is a destructive technique. As sample is completely destroyed, we do not recover the sample and therefore a destructive technique that utilizes sample totally. In many cases we have to require sample many times and therefore this is one of the most important disadvantage of this flame atomic absorption spectrophotometry. Students, this is about the different types of advantages and different types of disadvantages of the flame atomic absorption spectrophotometry. With our today's discussion, you can find out the answers of following question. Question number 1. What is interference? What is interference in flame atomic absorption spectrophotometry? Give the list of all the types of interference. What is spectral interference? What is spectral interference? Explain it with suitable example. Then explain the chemical interference. Explain the chemical interference. Chemical interference in flame atomic absorption spectroscopy with its remedies, with its elimination. And number 4, write a short note on self-absorption, and finally give advantages and disadvantages of flame atomic absorption spectroscopy. Student, with our today's discussion, you can find out the answers of these questions. With this, we stop here. Thanks for joining me. Wish you all the best. Keep learning. Happy learning.